Dr. Debabrata Goswami from Indian Institute of Technology, Kanpur. Dr. Deb Goswami is a professor with Department of Chemistry, IIT Kanpur since 2003. He obtained BSc from Jadavpur University in 1986, MSc from IIT Kanpur in 1988 and PhD from Princeton University in 1994. Before coming to IIT Kanpur, he was a faculty at the Tata Institute of Fundamental Research, Mumbai for 5 years. He did postdoctoral work at Harvard University and Brookhaven National Lab. He is Wellcome Trust Senior Research Fellow, has won many awards and honors including the prestigious Swarna Jayanti Fellowship in 2004. His research interests are femtosecond pulse shaping and adiabatic quantum computation. He was the organizer of the Quantum Computing Back Action 2006 conference held in March 2006 at IIT Kanpur, which has been dubbed as one of the most successful conferences on quantum computing in this part of the world. He has authored several research papers and popular articles and co-authored a book entitled Nano Computing, published by McGraw-Hill in 2008. He has close academic and research contacts with the Dalberg Educational Institute. He is also the collaborating PI of the MHRD Quantum Nano System Center from IIT Kanpur. Let's welcome Dr. Goswami.
Thank you very much for the nice introduction. So let us see what we can do, because I think whatever we have been talking about in terms of quantum computing, the basics are mostly covered, but for completeness I will start off with a few basics if there are any students who can still take something from there. So I come from an experimental world and I work with light pulses which are in the femtosecond region, and I am currently in the chemistry department, although while I was in Tata Institute. So we work on the area of time scales which are in multiples of 10 to the power minus 15 seconds, and in this time scale people expect that you will be able to specify the bond that you are going to hit of a molecule so that you can control it to a point that it will vibrate, and if this is how you could represent it, then this would be a very nice model to start off with your qubits and doing the kind of computation as you would like to, because this would be our logic starting point. Unfortunately, this is not what happens. After a few femtoseconds, this entire molecule vibrates, and this is what essentially any simple system, whenever you are trying to work with in a molecular system, that's how it works. And so the speciality of trying to localize the energy in a particular molecule is lost because of the entire molecule vibrating in its own randomness. And so our main aim has been to try to access the different kinds of possibilities that are possible to achieve the selective vibrational condition of the molecule, which would perhaps lead us to some logic areas also. So there are many different areas that you can look into while you are trying to do research at this level. And so one of the areas which is also kind of known as the holy grail in terms of chemistry is to specify a particular bond and do some chemistry with it. It comes under the area of coherent control. Today I will be talking about quantum computing. However, when you talk about pulses of light which are so short, it also has very high intensity. So you enter into the nonlinear domain of spectroscopy, and so we do a lot of nonlinear spectroscopy. And since the pulses of light, while interacting, even if they are not absorbed, can actually have other impacts, it can create a lot of thermal issues, and there is a lot of interest in terms of thermal lens microscopy, which is one of the areas which we work on. These are the areas I will definitely not tell you today now and make it a long evening. But there are other areas which we go into, which is a long list here. But to be focused, we will be talking about quantum computing. So just going back, although Paul Benioff was the one who rang the bell saying that miniaturization was one of the major reasons where we are going to a point where it is all getting statistical, it will become statistical. It was Feynman who basically looked at it and made that famous statement, there is room at the bottom, and essentially turned the problem around to be something which we pursue today, which is quantum computing, looking at it from a positive angle. It's like saying a glass being half full or half empty, and the point is that it turns out that the fact that quantum mechanics is so complicated and so difficult, and as you go down in terms of miniaturization, you are going to hit it, it's not going to actually end the computational world in the terms that we know, but it also starts a new beginning. And David Boyce was the first person to have in fact come up with the idea of universal quantum computer, where he proposed that the qubits required are almost of the order of the number of particles in the system. So you just saw a wonderful talk on the basics of quantum mechanics, so I don't have to go into details, but whenever we go into subatomic or atomic size or in the angstrom level particles, even up to nanometer scales, we will be dealing with minute objects where classical mechanics don't work. We will be actually using linear expressions, linear equations which are governed by the Schrodinger equation, and it's a system of laws which describes the behavior of such objects, and we just heard certain aspects and nuances of it which are very, very difficult. So let's see how we go ahead thinking about it. The very first thing is, as was discussed here, is that the state is unknown at any given time and changes whenever we try to observe it. And the simple reason for that being that when we are observing macroscopic particles, just like you are observing me and I am observing you, we are using the medium of light to make this measurement. And in that framework, the perturbation light produces on any of us is insignificant compared to when we talk about subatomic or atomic particles, because there the act of measurement, which is the interaction of light with the particle in concern, essentially changes whatever is there of that system. And so therefore it's physically not possible to know an unknown state of a quantum system. The moment you measure it, it's gone. However, several properties of these systems can still be manipulated and measured, and that is why we can do some aspects of it. So there are several reasons you would like to go to quantum. One of the most important reasons, however, is the reversibility, because quantum mechanics laws are all reversible. At least the ones that we will be using within the Hilbert space using unitary operations will be all reversible, and so reversible computation is the one which has the minimum wastage in terms of time, energy, etc. So that is one of the most important things. The other part which we all have been hearing so much about is that we are not going to deal with discrete states anymore. We will be having combinations and their compositions putting together, and these at the simplest level can be started off with superposition states, but you just heard something more complicated which will also be stated. But in simple mathematical terms, we can transform this entire problem into linear algebra by considering matrices. So by representing the spin or the quantum system by using simple matrices and vectors, we can write rotation matrices or the operators, which essentially gives rise to these kinds of tippings and the other issues, and we can write down an entire operation in terms of matrix manipulation, and that is essentially our system of linear equations. And at the end of it, we definitely need to define it, because without definition it creates a little bit of a problem. As of now, the most well respected definition which I found in literature is the fact that it is an open statement where hopefully everybody accepts this point, that it is manipulation of quantum mechanical systems for information processing. It's a wide enough definition which encompasses all the aspects of quantum computing that is being attempted, and so a quantum computer would therefore be a device which will process information in a quantum mechanically coherent fashion, and obviously the reason we would like to do is that there is some benefit, and so it could perform certain types of calculations far more efficiently than any foreseeable classical computer. And so your bit now is no longer a simple 1 or 0, but it will be a family of all possible situations under a sphere, which is essentially what we often known as the Hilbert space or something like that. And so all possible combinations are the ones which are possible. I will not be able to go into these details in this particular talk, but it is very important to note that the promise of a quantum computer is in terms of these basic points. The first one, which was proposed by Feynman back in 1982 and essentially fueled the idea of quantum computation, was to be saying that this is the best possible way to simulate quantum systems. Because quantum computing essentially uses quantum mechanical objects using quantum processing and the laws of quantum mechanics, it should therefore be able to simulate quantum mechanics in the most efficient manner. That was the argument, and that is the way things are. However, this is perhaps the most difficult part of achieving in terms of quantum computing, and none of us are anywhere near. This is perhaps the last goal that we will be able to achieve when we finally build anything of relevance to quantum computing. What we have managed to do to some level is to show that it can still do some exponential speed up in certain problems, for instance factorization of integers in their primes, and this was shown by Shor in 1994 because he was able to use the exponential space available because of the way he could write his algorithm. So this is an exponential speed up case that is there. The other one which is not exponential but still has a lot of speed up is the search algorithm, which was proposed by Grover in 1997, which shows quadratic speed up. It cannot access the same level of space, which same efficiency as the factorization has been able to, but it is still good enough to show quadratic speed up. In fact, the art of finding quantum algorithm is itself a research field, and I hope that that would be considered as one of the very important areas of research as we go along in this area. So one of the important things is to essentially know that qubits, as we have defined, is again based on the parallelism that we are considering with respect to the digital computer of today that we define, and therefore the qubits are the ones which only use two degrees of freedom. There is no real reason or restriction to keep it that way. In fact, there has been propositions to use something known as qubits, where not just two states but many more quantum states are being used simultaneously to start building a quantum computer or the logic operations based on that. However, it's like saying unless we understand the very basic parallelism, it is much more difficult to go to a bigger problem. So we stick to this qubit idea, which has been going around in this conference also, to use only the binary representatives of the two states. Now the advantage of having a qubit in the quantum mechanical sense is that we not only have the ground and the excited states or the spin up or the spin down states, we can have something which is superposition of the two basis states. So the basis states form one of the most important points where we can start the process, and it is represented very often by a state vector written in terms of a notation where we are writing essentially the vector arrow. If the basis of if the basis state for a qubit are written in terms of 0 and 1, then the vectors of the qubits are a linear combination of them, and these linear combination, the coefficients give you the probability. Square of those coefficients is the probability. basis states are chosen always to be orthogonal vectors, so that you cannot have, they are mutually exclusive and one cannot have a projection on the other. The inner product of the two vectors therefore are satisfied, which is that they should always be equal to. You can have any other basis state. It need not be a Cartesian coordinate. It can be any other rotated state also, and you can always write with respect to the other, write one basis set with respect to the other, and that is actually a very important part of quantum logic and operations, because there are many cases that you will not be able to find a solution in a specific basis state. You will have to rotate or go to a different basis state to do the work. Systems of many qubits are the ones which you just heard in the last talk, where you can combine not just one or two qubits, but you can have them combined in a certain way, and once you combine them, you can have an overall state of the system. For instance, this is a simple case of 3 qubits. So a 3 qubit combination can be done, and you can get the solution to those 3 particle system. Typically, the total answer is that it is a composite quantum system which is given in terms of the tensor product. And there is a shorthand notation which we always write, that is just we take the 1, 2, 3 and put them all together and write them within that notation. This is the outer product, and this is different from the inner product which I showed before, which always has to be 0. So this is by convention, therefore we write this 1, 0, 1 tensor product as 1, 0, 1 within that. And just to complete the story of superposition and entanglement, if you are going to have a combination of the states simply, which can be always written in terms of the original states, then these are all superposition states. However, when we combine them in such a way that they are only tensor states and they cannot be written down further back to their original states, then they become entangled. And that was the discussion that we had in the last talk, where entanglement was the key to the entire problem. Now, in order to run the quantum computer, like simple classical computer, you need the quantum gates, and in terms of quantum gates here, these are nothing but these matrices that we talk about, which essentially operate on the quantum states and give rise to the results that we are looking at. The simplest quantum gate is the quantum NOT operation, which just takes the state and reverses it. A single qubit gate, all possible single, and only those gates and matrices are allowed which are basically unitary in operation, so that they are reversible. So single qubit gates, all possible single qubit gates, and so there is a set of all these gates like that, and the C naught, which I will just show, form the complete set. So how can a state be visualized? I mean, when you apply a simple quantum gate, for instance, you can actually create equal superposition of two states, which is known as a Hadamard transfer. And if you do that physically, what will happen is, in terms of classical mechanics, you would be seeing either the ground or the excited state, whereas which you will be labeling as 0 or 1. But in terms of quantum mechanics, which is the Hadamard state, it will be an equal coherent superposition of the ground and the excited state. And the simplest 2-qubit gate, which also is the gate necessary to complete your the minimum number of gates possible required for quantum computation, is the control NOT or the XOR gate, in which the control bit remains the same, the other one is flipped based on the property of the control. And so it's the fourth pair states need to swap based on the the second and the fourth pair needs to swap with respect to the first. So in this talk, I will be focusing now on the implementation issues of quantum computer. And so what is necessary for our particular purposes is to be able to prepare the state, process it, and then detect it. Once we go through this entire process, we have actually managed to show a quantum computing operation. So that is the basic requirement of it. And this, often this processing of the state is termed as the quantum processor. Many a times when we are doing this, we often have also labeled them as processes which cannot be looked at, because that is one of the requirements of quantum mechanics. And since many a times these cannot be looked at, they are often clubbed into something known as an oracle, which is as if the solution is known and it's going through that many times. I have chosen to give you a couple of examples where you can look at some issues. You have been alluded to density matrices in the last talk also. This is one of the approaches to try to look at how you can evolve a quantum system. In this particular approach, what I have just done is I have also included a family of problems where not only just a single particular excitation or transition is being looked at, but a particular transition where all the applied field is able to coherently add is also being looked at. And this particular case is specifically possible to be achieved for a femtosecond laser because the time scale is so short, and if you have enough coherence between the states, then the pulse is able to add coherently to achieve an excitation which is far more than it is possible in a single minute pulse. So for instance, I have 800 nanometer light, which is very low energy as compared to the energy difference between the two states. However, because of the property of light addition which can coherently add, I will have a probability of making this transition happen, and this is a multiphoton transition. Under this particular domain, it is possible to write down the simplest case where these two states can still be considered as two-level system, and so the idea of a qubit still works in these kinds of multiphoton excited states where my light property will be the one where I will be manipulating it so that I can get my qubit to operate in the way that we would be like to do. And in order to, this is a convenient situation because what it does is many a times if you would like to excite a state to a point where it is going to lose an electron, let's say, and create a charged species, you can then look at the charged species in a much more repeatable fashion than it would have been otherwise. So this is one of the frameworks which can be developed to look at it, where basically a certain little approximation needs to be taken. One of the approximations taken is the fact that we are considering this process, which is in general a very low probability process compared to the direct excitation process. But generally what happens is when you are having 800 nanometer light and you are going to make a transition, let's say for a 400 nanometer light, which means that only 2 photons of these 800 nanometer light are going to add together to get to the excited state, you are not having any 400 nanometer light present at all to interfere with your measurements. And so whatever you will be measuring will be pure. And that's why this particular principle of experiment works. In going further, what we can also do is we can look at the property of the light in terms of the Taylor series expansion, where by considering the phase to be expanded in the Taylor series fashion, we can look at the phase property at under different conditions, and that gives rise to the property of light, instantaneous property of the pulse, and that instantaneous property of the pulse will create a specific impact on the system. And here is the traditional case which you have been already exposed to. Those of you who remember Professor Anil Kumar's talk on NMR, the simplest case where they always talk about an excitation is to say that you have an area of the pulse equal to something which will make it go to the excited state, and that area happens to be a pi area. The area under the pulse is pi, and under that condition it is a particular case when you get to the excited state. But there is a very interesting point here to note that when you have this kind of an excitation where it is an ideal two-level system, then the excitation will go through a situation where you are accessing. Now we are looking at the coherence terms, that means we are looking at the off diagonal terms of the density matrix, and here the real parts are all not changing, it is only the imaginary parts are changing. That means we are actually absorbing the applied field, and that is exactly what happens. When you apply a pi pulse, it absorbs the light and it goes to the excited state. So for a exact two-level system, there is no problem, because that is exactly what you expect. Unfortunately, in optics, there is really no two-level system available because of many reasons. One of the simplest reason is that any system is not perfectly isolated. If it is gas, it is moving, so you have a Doppler shift, and so if it is a laser which is going to go through it, it is going to have the same problem as a Doppler shift problem we have in terms of a whistle changing as a train approaches or something like that. So you will not be able to hit the same frequency all the time for the two levels, which means that you will not be having an exact two-level problem. And since that is the problem, having a pi pulse, which is the exact area which would have made the made the system absorb and make it go to the excited state, does not work for an optical situation. In fact, there have been papers in the 1980s where the title has been, there is no exact pi pulse for a molecular system. So the reason I put up these transparencies is for you to understand that when we are looking at the pi or the absorption case, it is always the imaginary component of the coherence or the off diagonal elements of the matrix which is the one which is responsible for this process. And had it been ideal, it would have shown all these Rabi oscillations and things like that. On the other hand, if we change the phase within the pulse, then the frequency component within the pulse changes in such a way that as the system starts absorbing a certain frequency and starts going up in the going up to the excited state, by the time it reaches towards the end of the condition, the frequencies that were available in the beginning, which would have actually brought it back to the ground state, is no longer present, because this is how the frequency is going through within the pulse. And so in this particular case, the population cannot go back down into the ground state. So even if it is not a perfect two-level system, it actually goes up to the excited state and stays there, because it does not have the other components of the frequency available for it to do so. Now, if this is how it is, then it will always create an inversion, no matter what kind of a system you do. But the important thing here to note is that you do not access absorption in this case, and this is what I want to show you when you look at the off diagonal elements of the density matrix. Here we are actually going to see the real part of the system being accessed and not the imaginary part. The real part, by the way, is the refractive index. So this is something which we know in spectroscopy all the time, which is called whenever you look at, so there is the dispersive part. So if you are looking at the complex nonlinear response or complex response of a system, linear response also, the imaginary part corresponds to the absorption and the real part corresponds to the refractive index or dispersive dispersion of the system. And so this is exactly what we see here, that the real part is the one which is being accessed here, and the absorption part, which is the imaginary part, is almost not there. And therefore for these kinds of systems, you can always go halfway also, and you can see exact same solutions. So here is this is what is known as the adiabatic process, which is slowly changing process, so that the field is changing and the system is able to evolve with it. And in this case, you are always accessing only the real parts, and the imaginary parts essentially don't change. So the reason for building this problem up for you is to say that although molecules are never going to be a two-level problem, you can always cheat the system and make qubits out of it. So that is because even if you try to use two electronic levels, there are embedded vibrational states which will come into the play and will not make it happen as a two-level system. And this is one of the tricks that you can use in optics, which will make it feel that it is going to go through a two-level system. So So here is again a model Hamiltonian where all the coupling terms are present, but yet by using these kinds of tricks we can make it believe that it's going to be a two-level system. And why is it important? It's also important because of the first picture that I showed you in the very beginning of my view graph, where I said that I was able to vibrate one particular bond of the molecule, and it was just in a few femtoseconds going away to the other vibrations. That was the exact same problem. This was the bond that I was trying to hit, but if I don't do anything actively to the system, it will always go out to these other states which are sitting there coupled. It's like a spring coupled with everybody, but if I am somehow able to make this spring move in such a way that it does not anymore resonate with the other states, then it will remain as it is. So these are the tricks which you can again use, which is like using the field being change of the field within the pulse, which will actually create this situation. So these are ways of proving that this is how it's happening. I will not want to disturb you with these pictures one after the other. It's just to prove that if you use the field changing halfway and then keep it right there, or you turn it off, then everything goes away. But as long as you can keep the field at the same place, halfway up, and when you have created a complete coherence and leave it there, then the two states are always formed in the right way. So this, by the way, in quantum computing sense, is a Hadamard transform that you have managed to get when you have put the whole state into the coherent superposition, equal coherent superposition of two states, in spite of the fact that you have many other states available to you. So this is exactly what I wanted to show, that within this period of time, this is the time in some units where you will find that the states are always in the two states of concern are in combination, which can be a Hadamard. So these are certain calculations which are shown. This, to be honest to you, I have also picked up a molecule which is an anthracene molecule which has many other states in fact available, but yet we are just going to access the two states and show that these things can happen. You can also make it more and more complicated, and yet it keeps on happening. The other interesting thing is that you can in fact create a very nice Hadamard state, a combination of many more states instead of just the two states here, because what you can do is you can actually play the same trick with not just two states but many states now, where all these other states are now being put into a coherent superposition, and the ones are not being used. So yeah, this is the terminology which has been used by other groups, where qubit terminology was used to show that more than two states are being used. So what I have tried to show you here in this part was to show that the real and imaginary parts, which I already said, are the ones which correspond to the absorption versus dispersion, and by coupling it appropriately through the absorption part, which is what is done typically in NMR, you can use an exact two-level system. However, in our case, which is optics, where there are many other states possible, you have to actually go through the dispersive route, and therefore adiabatic processes are much more robust, and that's how it works. So what we are now looking for essentially are known as control knobs. Being an experimentalist, we are actually looking for control knobs so that we can take a system and control it in one way or the other. It's like saying that we have a radio and we definitely need the knobs so that its volume as well as the station can be controlled or can be achieved. So the few things that you can do is you can actually do a spatial modulation so that you can put it somewhere and freeze it, one. Other option is to use the laser polarization, which is like to try to do some manipulation with it. And the simplest one of all, as we have already seen, is the frequency change within the pulse, which is the temporal modulation. So how important are those and how can we look at it? Let's go straight to the spatio-temporal part, where we will be using both the spatial as well as temporal control part. So first let's do the spatial control part. Now this is relevant because this is also something which is going to be very useful for all the people who have talked here today about using nanoparticles for doing their computation. Because if you imagine your nanoparticles who is going to do computing at some point of time, then you would need very specific control spatially, so that they, after they have done some computation, they are able to transfer the information next to each other. Today what we are thinking is that we will be coupling them through RF or other techniques so that they can come closer and do that. But there are many difficulties in these kinds of techniques. Spintronics is also another approach where this RF coupling is one of the ideas which is being thought about. However, if we can do a spatial control on top of the modulations that we are already talking about, then we will be able to finish a part of the algorithm, make it go to the next qubit or the set and start doing the next one. So in this context, I would like to bring to you the idea of using an optical tweezer. Now, optical tweezers are not new. This is just this was Ashkin had invented it back in the late 80s, which actually uses the intensity profile of the laser pulse, and it need not be any pulse laser, it can be any laser, however CW laser. However, it is important that it has a gradient which is slowly changing. A Gaussian happens to be a good one. And so for a Gaussian, as long as your particle is large, so that your wavelength is much less than the diameter of the particle, then you can just use a ray optics scheme. And in this principle, what you can show that it's if the refractive index of the particle is larger than the surroundings, which is typically what it is, you generally use beads of some sort to show this. Then what will happen is it's going to bend because of refraction, and you will have a restoring force coming. And by using these force lines, what you can show that you are actually having, you can take care of the scattering due to the Brownian motion by using a gradient force, and this can be represented by a spring mass system, which is also, in fact, there is something called a trap stiffness, which is the definition, which is just a simple harmonic oscillator model that people use. And people have used it in many ways, not only just by using refractive index schemes, they have also nowadays used thermal gradients to also get to these kinds of trap stiffness. If you go to smaller and smaller particles, you can actually come up to a point where your wavelength is even larger than the particle. Then you have to use the convention of dipoles. And however, at the end of the day, you end up producing similar results. You can actually create a dipole with a harmonic system kind of a principle and still get the same result. But mind you, the profile of the beam has to be Gaussian to have these balancing happen. Otherwise, it has to be a paraxial Gaussian mode. Otherwise, if you use a flat top Gaussian or almost a rectangular pulse, the trapping does not work. So this is in particular our trap. Now, the reason we have gone into our trapping is that we have actually used a pulse light. There are a few reasons why we ended up producing pulse light. One of the major reasons being that observing these traps as you go to smaller and smaller particles become more difficult. What we typically are looking for is a backscattering from the particle. Now, backscattering, as you are making the particle size smaller and smaller, gets more and more difficult. It is much easier if you have a fluorescing particle sitting there, but in order to access fluorescing particles, it is best to use a pulse light because then the efficiency is very high. So you can even look at a 2-photon fluorescence condition where any other system around, nothing will happen. When you have these are, by the way, it's the Gaussian beam is being focused to produce the trap, and so you will be achieving your intensity requirement for a 2-photon condition when you are using the focus light, and so it turns out that a 2-photon condition for a trap, pulse trap, is a very useful one. So this is what we have actually developed, and this is a design. This is a picture of the reason why you would like to do this. So this is like we are waiting for the particle to come and trap. So once we trap it, this is still looking at the backscattering light. You can see the backscattering light being present. But in this particular case, you can turn off the ambient light which is necessary to otherwise see this, and you can see a background free detection, which is very useful when you go to smaller and smaller particles. We are able to we have published the case of 100 nanometer particle, This is the case where we have already published it. However, we have managed to trap up to, this is trapped 100 nanometer latex bead. However, we have already managed to trap about 20 nanometer particles. These are all nanoparticles which are, and we have actually gotten some particles which are 2 to 4 nanometer size distribution, which we are currently trying. There is a possibility that we are also able to trap them. But mind you, we are using the same wavelength of light all the time. This is 800 nanometers. So our lambda to the d, the wavelength, the particle size is now orders of magnitude different and very far off from the diffraction limited size position. And so this is one of the ways to go down in resolution in some ways, because the resolution limit is given by 1 over lambda roughly. So in this particular case, the repetition rate, however, is very, very critical, because if you don't have the repetition rate correctly set up, then the time for which the laser is not present, the particle will go away. So it always works in a high repetition rate regime. Typical lasers commercially available are in the range of 50 to 100 megahertz, and in those time scales there is no problem. We have managed to work very well in that region. We call these things as spatial traps. So what happens is, this is like a potential in which the particle is being trapped and they are transiently being generated. So for instance, the trap is there, then again it's there after some time, say this is about 10 nanoseconds, and the Brownian fluctuations which occur within this time scale, we can show that it is less than the region over which the focus is. So in some ways, smaller the particle is, the easier it is, because those things, the fluctuations don't matter. Now, the other thing which is kind of interesting in this area, which I have already shown you but you might not have recognized, is that when you see these double steps, it essentially means we are actually putting more than one particle inside the potential. So it's almost like a particle in a box model where we are packing more than one particle. And typically for these particular experiments, we have specifically chosen particles which are not aggregatable. Because if they aggregate, then it will just grow in size and it will not be useful. So in this particular case, for example, it has gone up, and in this case, both of them came out simultaneously. But there are cases where we have seen this stay together, then maybe another one going, and then somebody came down, and then the next came down. So there were times when 2 or 3 particles in that spatial potential are sitting there and rattling around, which is very interesting to study in these kinds of cases. Okay. So the other interesting thing that we are also looking at is that for the non-centrosymmetric particles such as the BBO needle, you can produce second harmonic. So instead of looking at fluorescence, you can actually look at second harmonic. It's the same principle. High intensity of light is needed, and so with pulse laser that turns out well. And there, by using the polarization, we can actually look at, and this is what we have done, we have also looked at the rotation of the left versus right corresponding to the left versus right circularly polarized light, and by using a BBO we can actually see how they are rotating and what is going on there, speeds and changes in that. So all these other tricks which we can do. So it's some sort of a control that we are after in these kinds of things. Okay, so that we call it as a spatial control. Now we would like to go and add our temporal control to it. So now the temporal control on molecules. Now generally control in terms of molecule, as a chemist, typically these are all the macroscopic control parameters. Temperature, pressure, concentration, these are how it is. And there is also this catalyst. But typically catalyst is considered to be a microscopic control in the chemist term. In our particular case, we are going down to the molecular system, and we will be controlling with the help of laser, and so we can consider the laser part, laser infused, for instance, this is the fragmentation case. We can consider that to be in the microscopic domain, where perhaps in the simplest limit we can consider it to be a fragmentation which is being induced by laser. So it's in the catalyst kind of a principle. So that's what we are going to look at it. And what we are trying to look at is to see when we have multiple control parameters. So for instance, I gave you the example radio for the exact same reason. If I have only one knob on the radio, it's alright, I can only go and change my volume, turn it off. but very often I would like to go to another station. I am tired of only listening to one song. So what you would like to do is that you would have to have more than one control parameter. And what happens when you have more than one control parameter? It will be ridiculous if you keep on changing one channel and your volume keeps on fluctuating along with it. So you would like to have control parameters which are totally mutually exclusive. So we are after looking for mutually exclusive control parameters. Are there these kinds of control parameters? So the first case study was that of photofragmentation of I don't know the name of the molecule, some molecule which is large enough and undergoes fragmentation. It has some cyclic structure with some linear molecule. Anyway, our principle is to use the changing of the light frequency within the pulse. That is the principle. Laser technology wise, it's not very complicated. It's actually just a grating and a mirror combination which allows us to do this. It's a curved mirror with a grating combination. And you can look at the pulse characteristics to see that in fact it actually undergoes these kinds of things. So that I know you will believe me. So now here is this particular N-propyl benzene. So this particular molecule undergoes many different fragmentation possible channels, and when we look at it into our mass spectrometer, under the condition when the pulse is transform limited, that means there is no chirp there, we will be getting certain fragment distribution. Okay. So now when we change the property of the laser pulse, so this is negatively chirp pulse. So then that is basically blue to red or red to blue. That is how we define red or negative versus positive. So you see some other distribution, and when you look at it for the positively chirp pulse, then you see some other distribution. In order to summarize, let's say we look at it here, the purple one essentially shows only the second harmonic generation, which essentially is asymptotically falling on both the sides, showing the intensity effect. But what you will see, because as you change your frequency content property within the pulse, it also changes its intensity. So you do have an intensity effect, but that is reflected only by the purple graph. The rest of the ion field, ion effect are essentially selective to the frequency component of the laser pulse. And so you can see certain fragments are much more affected than the others, and so that is the effect of positive and negative chirps. Now, so there are reasons why this can happen, but the point is we can actually see some selectivity. So the next thing is to put in the second parameter. Say we put in the polarization parameter, because one knob is now clear, we have something which changes the fragmentation pattern. So now we put in the polarization parameter, and so we look at a simultaneous effect of chirp and polarization. What we now see is that overall ion yield changes. However, the relative ion yield which was changing with respect when we use the chirp case no longer changes here, and so this particular change is not going to affect when you are having the chirp also. So the fan out of these ion fragments happen when you have both the frequency component as well as the polarization changing, but with the polarization it's only a strong modulation of the entire field. Now this is partly because of the fact that in this particular case, because the field is so intense and the pulse itself is coming in one polarization, it is also an alignment issue because we have a mass detection on one side. So when the polarization is coming on one direction, it is much more effective in breaking it up in the direction where you are observing it, and therefore you see this kind of a peak with that polarization, whereas when you are coming horizontally, when it is actually just the least effective, then you are at the other place. However, it means that the polarization component is not interfering with your frequency component. And so this turns out to be one of the, in literature we have not yet found any particular case where there were two cases where they were able to come up with multi-parameter control where one is not affecting the other. So these are the two mutually exclusive control knobs that we have managed to show. Continuing on this idea of fragmentation to show control, I'll just give you one more example which turns out to be even more exciting, because this particular case essentially gives rise to only two fragments. So this, to chemists, this make a big impact. To us, it essentially means that we have only two different properties here. Now 2 is good for us because we come from the quantum world. We would like to have only 2 answers. So for us, this kind of a complicated system, which is very good for the chemist also, because this is some kind of a name reaction for which the 12th class students have to mug up their entire life. But anyway, this is a reaction where cyclization happens, and when we look at it the other way around, then it's the retro-Diels-Alder reaction of this dicyclopentadiene molecule, which gives rise to these cyclopentadiene. Yeah. So when you look at it, you have either the dicyclopentadiene, that peak, or the other one, which is the pentadiene. So when you look at it and you basically do a laser intensity, you know that how many photon process it is. It's roughly a 4-photon process. Now in this particular case, what we also did was we sort of looked at the mechanism, because we had to actually make sure that this is how it was working, and we sort of made sure that this is our pulse. This is how the production of the system is happening. We have two different data which is coming out. The two cyclopentadienes as well as the dicyclopentadiene, which are the ones which are coming here, and so we have all the time scales and everything that is established. But the interesting part is that the chirp effect on the parentyl as compared to integrated second harmonic and pulse width effect is going to be based on this data. So if we look at the dicyclopentadiene system, it is just showing an intensity effect, because as I am chirping, my second harmonic intensity is going down. That means my intensity, the pulse intensity is less. Turns out that the formation of this particular case is slightly going higher. However, when we chirp it, for the case of the pentadiene system, they show enhancement on one side, drastic enhancement compared to the other side, showing that it is very dependent on the way it is interacting with the applied field. And so this turns out that there is a strong controlling effect of, again, the chirp parameter on this chemical reaction. So it is not only the fragmentation of one single system that you can say that there is because the fragmentation process unfortunately yielded too many ions, and sometimes you can question that whether you can have any use out of that. But when you have only two things to look at, then there is a lot of hope. So that is what we are hoping that with this system that where we have shown that there is a major distinction, by this use we will be able to make some effectiveness out by doing our laser property. So what we have is this Fourier transform process, optical Fourier transform, where we take a laser pulse, put it through a grating and a curved mirror pair, and then recombine them, so that it actually in the Fourier domain we have the entire frequency components available to us, which we can modulate with an applied with a modulator. So in this case we can have a SLM, which is a spatial modulator, light modulator, or an acoustic-optic modulator. Acoustic-optic modulator has the advantage that this can be updated much faster. So we use this, and this is the currently modified system. We started off with this, and now we have the currently modified system, which is all reflective. As we go down in size of the pulse width, we have to go to our reflective conditions, and we are able to get to this complex added geometry where we can get the feedback of the applied pulse to exactly what we would like to have. So what I have tried to do here is to show you the applications in terms of quantum computing that we are trying to get to. There are other applications, as I mentioned, microscopy and others which have been used to apply for biological systems, but we are mostly interested in spectroscopic applications which could give us control over molecular systems to a level so that the logic information can be fed into the molecular systems and can be read out also. And with this kind of a connectivity, we are trying to see operations which make computational sense are able to be operated in this manner. However, in order to run this, we have all these other different aspects going on. Entangled photon microscopy is something which we are also hoping to look at it in the future, and that's why our microscopy angle, which is currently on biological system, would perhaps also get a lifeline from the quantum world that we are hoping in the later stage. I've shown you a lot of pictures. Here is a summary of some of those pictures. Pulsed optical tweezer I showed to you, and starting from pulse shaping to 2D spectroscopy, to interferometric microscopy, beam chamber, and then finally doing thermal lens microscopy. Thermal lens spectroscopy are all the different areas that have been happening. Our future direction hopefully is to converge on the idea of the spatial and temporal aspects, and we are hoping that in order to get a reversible region in experiments also, we would like to go to the point where we are doing it in a microscopic manner, because in the microscopy we have already shown that we can use multiple pulses to generate better higher results, better resolution, which will perhaps let us able to see our implications that we are trying to do. Because at the end of the day, when we have finished something, we should be able to tell it and be able to repeat the process. With that, I would like to thank you for your time.
Yeah, it's an impressive collection of work you have there. Have you tried to feed back in a genetic algorithm type approach to maximize any of your peaks that you're trying to reach?
Well, one of the first things we did in terms of the pulse shaper when we were working on is that we fed back our optimization. So we have actually set up a genetic algorithm feedback loop for our pulse shaper, and the simplest problem we looked at was second harmonic generation. So we were maximizing the second harmonic generation by a feedback loop system with the pulse shaper.
Yeah, what I mean when you're trying to get your Hadamard gates and all of these things, that's a little bit more complicated than have you?
For the gates at the level of systems, I think we have the biggest difficulty is that I don't think we can define an algorithm as of yet. From whatever we have said as of now.